Here's a different type of example about work. A heavy rope lying on the ground has mass 12 kilograms and is 8 meters long. Assuming the rope has constant density along its length, how much work is required to lift one end of the rope to a height of 5 meters? The first thing I want to deal with is this constant density along its length. Okay, so all I'm really thinking is my rope is 12 kilograms divided over 8 meters. So the density is 1.5 kilograms per meter. Now my overall plan for problems like this is, imagine I have this rope. Okay, this is the ground. Right? And I have this rope. Most of it's lying on the ground, and then I'm picking up one end that's going straight up in the air. Now, the part of the rope that hasn't left the ground really doesn't matter for this problem. The part that I'm focusing on is the part that I have lifted into the air. So I'm going to split up the rope into small sections. Okay, so here's a little section of rope, and I'm going to say that the width of that section is delta x. And then I'm just going to put some axis here. I'm going to say that down at the bottom, this is x equals 0. Up at the top is x equals 5. And then the height of this slice is x. Remember, this is a variable because this slice can move up and down the rope. Okay, so for one slice, of the rope, the mass of the rope is 1.5 kilograms per meter times the length, which is delta x. The force on that section of rope is mass times gravity, which is 1.5 delta x times 9.8 meters per second squared, which gives me 14.7 delta x. Okay, and then the work done to lift that one small section of rope is the force times the distance, which is 14.7 delta x. And then the distance this little slice needs to move is from x sub I up to 5. So 5 minus x sub I. Okay, now what we need to do is add up the work that has to be done for all these little slices of rope, right? Each of these little slices has a certain amount of work. We need to add it all up. So we're going to sum from I equals 1 to n, 14.7 times 5 minus xi delta x, because that's our expression for the work for each slice. Okay, now we're just going to let the number of slices, the n, go to infinity. Okay, well, if you imagine sticking a limit as n goes to infinity in front of this, this is really a Riemann sum. Limit of a Riemann sum gives us a definite integral. So we're integrating from 0 to 5, because that's where the slices start and stop, is x equals 0 to x equals 5. We're integrating 14.7 times 5 minus x dx. And then we just evaluate this integral. So we have 14.7 times 5x minus 1/2 x squared, evaluated at 0 and 5, which is 14.7 times 25 minus 1/2 25. When I plug in 0, we get 0. And overall, this gives me 183.75. Because this is work, our unit is joules.